Today in a May lead code challenge, we got a problem of count square submatrices with all one. The problem statement says that given a m into n matrix of ones and zeros, return how many square submatrices have all ones. And let's go to the example. The matrix, this is our input matrix, and the output comes as 15. The explanation says that there are 10 squares of side 1 which is visible. You just add all the ones. There are 4 squares of side 2. So this is 4 squares of side 2, and then there is 1 square of side 3 which is visible from this first row, this one. Okay, and then total number of squares is 10 plus 4 plus 1, 15. In the second example, how many we have matrix, and then the output is 7, and explanation is there are 6 squares, 1, 2, 3, 4, 5, 6 of side 1. There are 1 square of side 2 which is from the first row, and first column. Yeah, and total number of squares is total 6 plus 1, 7. The constraints are array length is between 1 to 300. Okay, the matrix is never null or zero. It always start from 1 to 300, and the values inside the matrices are always 0 and 1. Okay, how to approach this problem? The first thing which will come to our mind is just loop through all the rows and columns of the matrix and think that this is a starting point, and check all the way through till the end of row and all the way till the end of the column, and just check if it has 1. It will just keep adding the squares. This approach is a brute force approach, and it will give us, because we are looping through the matrices, it will give us big O of n square, and inside each loop we still have one more loop which will go till the end of the row or a column. So it will result it in a big O of nq solution, which is not optimal solution. And also you will see that we will do the repeated calculations in our brute force approach. So we need to think a bit more about optimized solution, how to go through the optimized solution. Okay, every time we are in a place where we think that we have a repeated calculations going on, we are doing same things all over again and again, we should start thinking about the approach of dynamic programming. Dynamic programming is something where we break the big problem into smaller sub problems, and we calculate the smaller sub problems, and then this smaller sub problems actually lead to the sum up to a bigger problem. So let's start with our solution. How do we think about it? This is our matrix. Let's start the base case. Let's start thinking that what will happen if this one if this point was the end point of the square matrix which has all ones. So in that case, let's see this one. So if this was the end of the square matrices, how many matrices will be calculated? And it is 0 because there is nothing, and it's for this row, how many square matrices will be generated if this was the end point of the square? And we will see that it's 1, and this will also be 1, this is also 1. For the 0 row and 0 column, it will be exactly same as what is there. If it is 0, it will be 0. If it is 1, if it is 1. So for the 0 row and 0 column, we are pretty much sure what it will be the result. Let's start thinking with the first row and the first column, this part. How many squares could be generated here? The number of squares which will be generated here will be, we will check the calculated value one row behind, and the one column behind, and one row behind, and one diagonal behind, and the result will be minimum of all these three plus 1 if it is 1. So at this point, how many square matrices could be generated if this was the endpoint? It will be one. It will be one, because this is 0. Okay, how many square matrices would be generated if this was the endpoint of that square matrix? So this is already 1, and then we will take the minimum of one column behind, one row behind, and one diagonal behind, which is 1. So it will be 2, and in a similar fashion it will be here it will be 2. So let's see, let's start with we will have the result matrix, which will have the same number of rows and columns. And how it will look like: the rows will be, the 0 row will be always same, and 0 column will be always same. Okay, what will happen at this point? We will take the minimum of 1, 1 and 0. What would be result? The minimum is 0, and it itself is a 1, so it will become 1. 0 plus 1. At this point the minimum is 1 and is itself 1, so it becomes 2. At this point the minimum is 1 and it is 1, so it becomes 2. At this point it will be, the minimum is 0 and it is 1, so it will become 1. At this point the minimum is 1 and itself is 1, so it becomes 1. 1 plus 1. And at this point the minimum is 1 and it is itself 1, so it will become 1. So the total number of submatrices with ones from this matrix will be just addition of all these rows and columns, that is 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what is the answer? I missed at some point. Wait. This is the minimum of 1. Oh, this one should be 2. And this one should be 2. Yes, and yeah, I missed it because the minimum of 2, 1, 1 is 1, and then I add 1. So now it will become 15. The minimum here will be 2, 2, 2, 2 plus 1, that is 3. Now it is 15. Yes, this is the explanation. Let's start with the implementation, then it is more clear to us. We will declare our basic variables. Number of rows is equal to matrix dot length. Let our number of columns is equal to matrix 0, since the rows and column always starts with the 1, we don't have to worry about a matrix which is null. And then let's start square count is equal to initially to the 0. Okay, let's declare our second matrix, which is of same row and column of the matrix itself. So let's say it as a dp, and which is equal to new array of size rows dot fill it with 0, and then map through each row, and for each row return array of size columns and fill it with 0. Okay, so this is it. We already have a matrix. We will start looping through this matrix. So for let I is equal to 0, I less than rows I plus plus, and then for the columns we will declare it as a j, which is equal to columns, and then j plus plus. Okay, so what happens for the 0 row and 0 column? So if I is equal to 0 and j is greater than equal to 0, what do? We will simply copy the matrix into the dp, so it will become dp 0, and then it will become j, which is equal to matrix 0 and j. We will do the same thing for the first column. Let's make it else if condition, where j is equal to 0, just interchanging the rows to column, and the I is greater than equal to 0. Becomes 0, it becomes I, it becomes I, and it becomes 0. Okay, so we are in this if else condition, we are filling the 0 row and 0 column. After that, what will happen if matrix I and j is there? In that case we will do dpij, dpi and j is equal to math dot mean of dp I minus 1 j dp I, and the last diagonal I minus 1 and j minus 1, and we need plus 1, and this will give us this will fill up the ith row and jth column of the dp matrix. And after this else condition, we will simply increase square count plus is equal to dpij, and at the end we have to return our square count, return square count. Yes, this is our solution. The way we discussed it, we have a matrix of same row and column. We are filling it up based on whether it is 1 or 0. If it is 1, we will simply take the one row behind, column behind, and the diagonal behind, and we will add plus 1 for that. Let's start running the code. Hip out of memory. So it should be j, sorry, it should be j, and let's start. Okay, this gives the right result. Let's start with the second example. Let's try submitting the code. Yeah, it got accepted. The time complexity for this is big O of n square, and How do you like this solution? Do you have any ideas of optimization? How can we make it more faster than this? Please write me. Thank you. See you soon.